Okay, as I just sent you an invitation, or no, I just sent you an email. Let me bring that down here. Share my screen. Okay. All right, the thing that I told you on Wednesday bugged the heck out of me. Hopefully you can see my Admiral Studio screen. Whenever you use %F in a print statement, it simply printed a question mark and not the value. And I had shown you a workaround on Wednesday where we took the fractional part and took the integer part of a result and sort of made it work, but it was a really sloppy procedure. %F can be made to work, and it is not real clear in the documentation for the AVR how to do it, but Google, or actually DuckDuckGo, provided a way to do it. And it is a case of, well, I'm just gonna hide the floating meeting controls that you can't see. You've got to go to project and properties. Okay. And then the steps were there. Tool chain, AVR linker under general. This box is normally unchecked. Use the vprintf library. Make sure you check that box. And then the next step, which I'm going to go back and cheat here.
It's miscellaneous.
Miscellaneous other linker flags. Okay. Under miscellaneous, this is normally blank. You type in -lprintf_float and Control S to save this. And then, see, is this still plugged in? Yeah, then we can just demonstrate it. Let's go back to here. Start with our debugging, and I'll open up PuTTY. While that's downloading. It's at 31% downloading.
Professor.
Yeah.
So the other day I was running the program. My code was mostly the same as the one from the presentation, the last lectures.
Okay.
I tried running it and on PuTTY, and I got nothing on there, not even an indication sign.
Okay. I mean, things to check if that happens, so you don't even get anything out. A thing to check is there is no magic way to do this. You'd need to set a breakpoint probably at the put character routine.
Okay.
And when you're using debugging, it's probably a good idea to do no optimization. There is a flag supposedly to make debugging great. My experience is that does not make debugging all that great. No optimization is far better. So set no optimization at all. And then you've got to put a break
What?
at the
Where would I put no
character routine.
optimization?
Say again?
Sorry. You said no optimization. How would I set that?
Oh, project properties. Under compiler, there's an optimization flag right there. Or optimization, I don't know, selection.
Set to none?
Yep, and then all of these are, I think the normal default one is 02.
Okay.
Optimized debugging experience, supposedly, according to the documentation, makes debugging a pleasure and breakpoints wonderful. My personal experience is that is not true. None is what I find most useful for debugging.
Okay, thank you.
My suggestion is set that to none. And then just to close the loop, you can do a, I don't know, 5 plus 3 and you get 8, and you do all kinds of stuff. The thing I showed you last time, normally if you do sine squared x plus cosine squared x, you should get 1. That's a trigonometric identity. So you type that in, and lo and behold, you get almost -1. And I looked at that and I went, that's really not correct. If you do sine 30 squared, oops, not, okay, let me try this again. Sine 30 squared plus cosine 30, darn it. A problem with this is if you hit backspace, it messes up the parser. So 30, because the backspace always goes into the buffer. Plus cosine 30 squared. All right, that is also, I mean, basically taking sine of 900 degrees plus cosine of 900 degrees. And that's also going to give you almost -1. So at that point, I said, it sounds to me like this parser, which again, you're not responsible for fixing this. I've looked at a couple of ways to fix it. It's which then breaks it in other ways. But if you do sine 30 and then in parentheses squared plus parentheses cosine 30 squared, then you get the value that I would expect from that identity. So the parser has a little bit of a bug in it. If you were going to try to sell this as a calculator type program, you'd want to rethink it a little bit. And what I noticed is if you type that, that works perfectly okay and doesn't complain about it at all. So really, I looked at forcing a function to be followed by an open parenthesis. I did an eat open paren if you looked at that parser routine at all. And that fixed some stuff and broke other stuff. So it needs a little more work, but for the most part, I'm interested in addition, subtraction, multiplication, and division.
I'm more impressed you got 30 to the 20th to not overflow.
Keep in mind, it's floating point, it's not integers. So you can do like 2 to the probably 40th, maybe even more. All right. And keep in mind the limitation on a 32-bit float is roughly plus or minus 10 to the 38th power. But there's only, how many? There's only about 7 to 8 places of precision. So I see 2, 4, 6, I see 8 significant digits, and then everything else is 0. So if you were to do this on a calculator with integers, you'd find it probably came out to something else, especially if you did like a TI-89, TI-92 that will do exact type calculations. So it's close, but this is, my guess is that's not correct.
Yeah, it's a little bit off. The TI-84 plus is saying it's a few digits off past the 5th decimal place.
Yep, that makes sense to me. The other thing that I noticed about this, if I do like 2 to the 8th, right, you get 255.9999. Now 2 to the 8th is 256. I understand that. But this is using the power function. And with 32 bits of precision, it just isn't that accurate. So again, if this were a real calculator, you'd probably want to look at having an integer mode or a float mode or something like that. Okay, but the main idea of this lab is to do input and output with the UART. Okay, questions on anything else there? Okay,
So
then
I don't need to fix the parser.
you do not need to fix the parser. If you as an intellectual exercise want to take a look at it, be my guest, but if you can spend time doing other stuff, that's probably preferable.
We might try it over the summer. We have the boards anyway.
Okay, yep, yep. All right, today then, we are going to look at a new concept known as analog input. Most of everything you've done in digital logic and in this course is ones and zeros. It's either 5 volts and 0 volts, or if you're working with some technologies, it's 3.3 volts for a 1 and 0 for a 0. If you're working with RS-232, it's minus 12 for a 1 and plus 12 for a 0, but it's discrete voltages. You might, or you will at some point, want to measure smaller increments of voltage. Okay, for example, I don't know how exactly this is going to work, but let me hold that up. Let me put a piece of paper behind it so the sun doesn't shine through it too. All right, that right there, you see a, okay, and I know circuits is not a prerequisite for this course, so if this is the first time you've ever seen anything like this, that's okay. But that symbol represents a potentiometer or like a volume control. A volume control in our case, we're going to treat it as a resistor. And on one side, if I can put my finger there, on one side, we've got 0 volts connected to that resistor. On the other side, we've got 5 volts. And one way to picture this is just a bunch of high resistance wire that's wound around a non-conductive core. The potentiometers on your board, or the volume controls on your board, are 10K. So we've got a 10K resistor connected between 0 volts and 5 volts. Now, I know some of you haven't seen Ohm's law yet, but I can't actually read it on my, maybe I can. Let me make my screen a little bigger. Okay, yeah. There's a thing called Ohm's law, V is equal to IR. When you get the circuits, you'll see that a lot. Or I current is equal to V over R, or 5 over 10K, or 0.5 milliamps. So 0.5 milliamps, that's 0.00005 amps, is always flowing through this resistor. Now, is that a lot of current? No. I mean, your average computer probably takes close to 1 amp. This takes 1 20,000ths of that, I think, something like that. The special thing about these potentiometers of volume controls is there is a third thing known as a vapor arm, which can slide along this coil of wire. So if I have slid this third arm, this vapor arm, all the way up to 5 volts, on the vapor arm, I'm going to get 5 volts. If I slide it all the way over to the 0 side, I'm going to get 0 volts on that vapor arm. If I'm right in the middle, I get about 2.5 volts because there's a pretty linear drop as I go from the 5 volts to the 0 volts across that resistor.
Is the putty supposed to be doing that?
Is the putty supposed to? Oh no, the putty. I'm leaning on the keyboard, so let me. Let's see. Let's just close that. And yeah, if I'm leaning on the keyboard, that's what the issue was. I'm sorry if that's distracting. So if let's see, let me. Okay, forget about that. I will make my window bigger too. Let me stop sharing the screen. Okay, yeah, then I can see this better too. All right, so now if I connect that vapor arm to any bit on port C, I can have a differential voltage on that bit of port C. It can be anything between 0 volts and 5 volts, depending on how much I turn that potentiometer. Now, why would you ever want to do something like that? Well, one example is maybe you want to have some sort of a volume control or adjust the brightness of a light. And you, in fact, the last lab you're going to be doing is going to be doing exactly that. The other possibility, see where I wrote it on this piece of paper. Bring that back a bit. All right, there is a device known as a thermistor. we have resistors which are fixed in value, and a thermistor is a resistor that changes with temperature. So I could conceivably put a circuit with 5 volts at the top, then a thermistor, another resistor, maybe 10K, and it down to 0 volts. With those two resistors joined together, I could connect that to any bit on port C. Now, what exactly does a thermistor do and how does it work? Well, a lot of thermistors, is a common thermistor that measures 10K in a temperature of 70 degrees Fahrenheit. If the temperature is 0 degrees, I'm kind of reading this on the screen. Is it? Let's take a look there. Okay, it's 85K at a temperature of 0 degrees. It's 3.7K at a temperature of 120 degrees. It's not exactly linear, it's close. There are tables which you can find on the internet of for thermistors. But if this resistor was 10K, if this thermistor was 10K at 70 degrees, and this was 10K, we'd have 2.5 volts. This is a voltage divider circuit. If you have had circuits, if you haven't, don't worry about it. If this was 300K, was very cold, that's still a fixed 10K. This is going to be much closer to 0 volts. It's probably going to be about 1 volt. And we could measure what that volt is. And there is a device called an analog to digital converter built into the 328PB chip that can measure the analog voltage and change it into a bit pattern. All right, so the one that's built into the 328PB is in fact a 10-bit A to D converter. So how precise can I get, and this would be where a board would be, a whiteboard would be really nice that I could actually write on, but how precise can we get a reading between 0 and 5 volts with 10 bits? Okay, well, how many possibilities is 10 bits? That's the first question. Let's see, 8 bits is 256, 9 bits would be 512, 10 bits would be 1024. Okay, so I could get to, I have 1024 different possibilities, 0 to 5 volts. If I do the 1024, or rather if I do the 5 volts, pulling out my calculator here, 5 volts divided by 1024, I get about 5 millivolts, 4.8 millivolts per step. So with the A to D built into the 328PB, if my range is 0 to 5, I can measure increments of about 5 millivolts. If that's enough for your application, that's great. If you need a 16-bit A to D, then you might need to do an external chip or you might need to use a different processor. So we're going to look at how do we access the A to D converter. The first step is we are going to go to the data sheet. So let me go to the data sheet and share my screen. Hello, data sheet, where are you? There we are, okay. There's the good old data sheet. And let me share my screen again. Okay, here we have the data sheet. And let's go down to chapter, whatever it is, 28, analog to digital converter. It is worth looking at this. And some of the features, 10-bit resolution. It is very accurate. It takes about between 13 and 260 microseconds for it to do a conversion. So, okay, 260 microseconds. You always have to ask yourself the question, is that a long time? Right, well, compared to what? 260 microseconds when your clock rate is 62.5 nanoseconds. Yeah, that's quite a long time. That's, I don't know, 4,000 clock cycles, something like that. So potentially it takes a long time to do a conversion. We are not going to use the interrupt mode for the A to D converter, or I'm not going to force you to use it. We're just going to tell it to do a conversion, then we're going to wait till the conversion's done. And if there's other stuff that needs to go on, then obviously you might want to look at making it interrupt driven. But just like you can poll the UART that we looked at, or use it in interrupt mode, and you can poll the timers, or you can use them in interrupt mode, the A to D is the same thing. You can poll it, which is all we're going to do, or you can use it in interrupt mode. If we go down to register description here. Okay, first we're going to look at this, each of these registers. All of the register names begin with AD, and multiplexer selection register is the first piece of this.
No, not the multiplexer.
It is a multiplexer, yep, because there's only one A to D, which we are going to, which you can route any of these. Well, I know it looks like there's 16 channels here, but really it's only 6, I believe, right? 0 through 5. Yeah. Really, there's only 6 pins that come out. In some versions of the 328 series or the Atmega series, there are not 16 pins, but there's more than 6. We'll look at that in a second. All right, I just need to get my notes here. Okay. The reference, we are going to use the internal reference. That's the simplest way to use it. There are a couple of others that give you more precision. They take some external components, but we're just going to use the internal analog reference. So that's going to be 0, 0. I take that back. 0, 1. There's a, oh, we did put a capacitor in. Wait a minute. Let me just have a look at this board. Okay, we're going to use 0, 1 actually. Okay, on the board, they basically have there's an analog reference pin, which is at 5 volts with a filtering cap, which gives you a little bit more accuracy. The next, so that's these 2 bits, we're going to make 0, 1. The next bit is left adjust. If we are using this in normal 10-bit mode, we have to return the result in 2 8-bit registers. One of those 8-bit registers is going to be the lower 8 bits, and then the other 8-bit register is going to be only have the up or the lower 2 bits used. That would give me the full 10 bits. There might be a time when you don't care. I had said the accuracy was about 5 millivolts. You might not care that the accuracy needs to be 5 millivolts. Maybe 20 millivolts is close enough. In which case you might want to ignore the lower 2 bits. There is a left adjust, which takes the 10-bit result and shifts it to the highest 10 bits of what is effectively a 16-bit register. So you can just read the high byte of that register. You get the most significant 8 bits. And the advantage is you only have 8 bits to work with. The disadvantage is it's 1/4 as accurate as it would be otherwise. So sometimes it depends on whether you really need all of the precision of 10 bits or if you can get away with just 8 bits. And I'm going to write some code. We're going to look at the trade-offs here. Next is a MUX selection. And I told you there were 6 inputs to the ADC. They'll port C0, C1, C2, C3, C4, C5. C6 and C7 are not brought out. We'll look in a minute if we've got time. They're not brought out to the board. I don't believe they're actually accessible on the chip. 8, if I put 8 in, that is a temperature sensor inside of the 328. This is not particularly accurate. I mean, it will tell you if you can fry an egg on the chip or if you're in the Antarctic, but you can look at some of it and expose it to different scenarios. It's not real accurate, but it is good for, is your chip about to melt? There's also a couple of special ones if you just want to check your A to D for accuracy. One is a reference of 1.1 volts, and the other is a reference of 0 volts. So that's the first register in the ADC. Let's look here. Okay, there is only one axis and control register. Actually, I take that back. There are actually 2, but only one that's real critical here. This is A to D enable. Again, just like almost every other peripheral, if you don't need it, it makes sense to keep it or leave it disabled because it saves you power. So if we're using the A to D, we need to write a 1 to this bit. This ADC, I'm going to write a 1 to it, and that says start a conversion. So whenever you write a 1 here, you'll start a conversion, and then based on the IF flag here, when this flag is set to a 1, that means the conversion is complete. So really to run this, I need to obviously enable it, set up which channel I'm looking at, write a 1 to that bit, and then check this bit, check this bit, check this bit. When the conversion is complete, this bit will be set to 1, and there will be a valid value in ADC H and ADC L, the data register mentioned up here. Okay, ADC L, ADC H are 2 8-bit registers that are going to hold the value of the conversion. Right. If I write a 1 to this bit, it's going to continually trigger and continually do conversions. That takes more power. So if you were running this off a battery, the battery would not last as long. But if that's what you want to do, you can do that as well. The ADIE bit is if you are using interrupts and you set this bit, an interrupt will be generated when this bit is set. You would need an ISR. You'd need to go back to the chapter on interrupts to see what the exact text is for the interrupt routine is going to be named, or where the vector is if you're doing an assembly language. We're not going to be using interrupts here. All right, the prescaler select. We have a table. if I, let me just look at my notes, make sure I say this exactly right. I didn't put anything in my notes. All right, prescaler. The A to D does successive approximations. There, again, I think at some point you actually do a lab where you build an A to D, at least you used to. If you can picture a, let's see, a counter that can count up or count down, and that's feeding into a D to A converter, a digital to analog converter. The output of that is being fed into a comparator with your unknown. Depending on which one is higher, your counter will either count up or count down until the two things match. And then that is the correct, approximation of your analog signal. Whatever's in the counter at that point is what gets written into the ADC-H and ADC-L registers. You can control what sort of increments that counter works in. For the most part, 128 is going to result in a faster conversion than anything else. And I think I put 128 in the example. Yeah, 111. All right, so that's that register. Okay, the high and the low registers. Note that depending on the left adjust result bit in status register A, if it's 0, the results returned lower 8 bits in ADCL, the upper 2 bits in ADCH. If the flag is set to 1, left adjust result, it returns the upper 8 bits in the high register, the lower 2 bits in the low register. So if you just read the high register, you get 8 bits worth of information, the 8 most significant bits, and you're dealing with 8 bits. All right, the only thing that is critical in register B here is, let's control register. This is going to be a 0. What are we triggering on? 000 says we are triggering on, well, we're free running. Did I put 0 there? Yeah, okay, we're free running, which means once I set it going, it's going to do a conversion. I could tie it to external interrupts. I could tie it to a counter. I'm just going to put it in free running mode. All right, so with that as a prelude, let's see if we can quickly write a little bit of code to do something. I'm going to close this solution, and I'm going to start a new project. 263 projects. I'm going to call this ADC example. Okay. Now, what I am going to do is I am going to, for the moment, leave the main program as is, and I'm going to write a function. I'm going to call it analog 16, analog read 16. And really, I'm only reading 10 bits, but it's going to be 2 words, and I'm calling it analog read 16. Okay. There are, I guess, 16 channels I could read from, of which 6 are brought outside the chip. So I can specify a channel. 0 through 6 is all that makes sense. But I'm going to get 256 possibilities there. All right, I'm going to say AD mux is equal to the reference I'm going to set to, I'm sorry, 0, 1, not 0, 1. I'm going to OR that with a 0 in my left adjust result bit. That means it's going to be right adjusted, the 10 bits. And I'm going to OR that with whatever comes in from the routine, shifted left by mux 0 bits. Now mux 0, there's going to be a symbol that's 0, so I really don't need that there, but for documentation purposes, not a bad idea to put it there. ADCSRA, status register A. This is analog enable. So I've enabled the A to D. I am going to put a 0 in that ADSC bit, which is the start conversion. I don't want to start a conversion right now. I'm going to say don't auto update. I'm going to say I'm not using interrupts. Well, okay, I'm not using interrupts. And in terms of the scalar, I'm going to do 0, whoops. 0B111. TPS0. I would encourage you to go back with these parameters, look at the data sheet, see if they kind of make sense.
Your code has an issue on the line above ADLAR.
On the LAR?
No, on the AD mux in the second parameter, you only have 1 caret.
Thank you, yes, okay, that becomes a logical expression. I was looking at it going, I don't see any way here with underlines, but that would have caused me grief. Thank you. Okay, the status register B, the only thing I need to worry about, and it would actually default to this. I'm going to set that to 0. And now, to start a conversion, I write a 1 to this bit. So I'm going to write a 1 to that bit, and then I'm going to wait until the bit I didn't show here, the ADIF, I'm going to wait until that is a 1. So here's what I'm going to do. Let's see, ADC status register A, or equals start conversion. Okay. Now,
Professor?
Is he frozen?
Oh, dear.
Hello.
Oh boy, the darn thing.
Well, we're
Well,
still here. It's just his connection that's bad.
okay. Well, I guess we'll just have to sit and wait until he comes back to us. Oh, now Michael is the host.
Right.
Oh. Hello, Professor.
All right, I don't know how long I was talking to myself, so.
Just a few seconds.
Okay, is the screen still shared?
No.
No.
Okay, let me share the screen again. Suddenly I see a box that says Zoom is reconnecting. Okay, now is the screen being shared?
Yes.
Yes, we can continue. Yay.
Okay, that was a new experience. All right. So I don't know, let me just talk about this again. This loop right here, I have started the conversion by means of this line. I write a 1 into that bit of status register A. I then am waiting, I need to wait until this bit, ADIF, becomes a 1. So I'm saying if the status register ended with that bit set to 1, if that's 0, means this bit has not yet been set to 1. So I'm simply going to spin and do nothing. Once I come out of that while loop, in ADCH and ADCL, I have the 16-bit result. So I can say return DC. DCH, DC, yeah. That's my whole routine here. All right. Now, what can I do here in this while loop? I'm going to say, I'm going to declare a variable up here called int, I'm going to do uint 16 underscore t result. I'm going to say result equals analog read 16. Let's read channel 0. Channel 0 is what I believe the rightmost pot is connected to. We'll verify that for sure in a second, but I believe the rightmost pot on this board is connected to channel 0. Plug this into here. Right now, if I had a nice display working or something like that, I could conceivably display the results of this read on the 4-digit 7-segment display. Since I mailed out every completely working board that I had and I haven't got a display shouted onto mine, I'm going to do that. I'm going to come along here and I'm going to put a breakpoint. I'm going to say port D equals 0xFF. That's more just so I can stop. Actually, I'm going to say port D is equal to result. So I can stop and check what the value of result is. All right, I'm going to do a couple of things here. I'm going to say properties, optimization, don't optimize at all. I am also going to set the tool to be that and that. Go back to main and say, start without debugging. Boy, it worked. That's pretty interesting. Okay. Except I don't want to start without debugging. I want to start debugging and break. Okay. I'm going to set a breakpoint at this line. So then I'm going to hit F5 to run this. And all of these potentiometers are all the way to the left. So we hit F5. Right. Let's set a watch variable here. The moment result is 0. Right. I'm going to take the rightmost pot. See what I'm doing here? Let's see. I'm going to take the rightmost pot, and I'm going to turn that all the way to the right. And I'm going to hit F5 again to continue running. Hey, look at that. Result changed to 1023. That's all 10 bits set to 1. So I've read that it's now got 5 volts on it. I'm going to do my best, and I'm going to say, so I'm going to set this about to the middle. I guess is right about, I think it's right about there. I'm going to hit F5 again. And I get 536. Exactly in the middle would be 512, 511. And that's pretty good. Right, so I can turn it down to about a quarter, hit F5 again. 168, I was looking for 256. I probably turned it a little past a quarter. If I go up a fraction, hit F5 again. Okay, 286, we're getting there. What do I have now? I have a way to read an analog voltage, anything between 0 and 5, and change it into a digital value that I can use within my code. You could use that for a humidity sensor, a temperature sensor, a potentiometer, anything that gives you a discrete voltage. The rightmost potentiometer is potentiometer 0. The middle one is 1. The leftmost pot is channel number 2. 3, 4, and 5 are actually brought out. I guess they're brought out to the explain board. They're not actually used on the 328 board. Okay, questions on that? Ultimately, what you're going to be doing is reading these potentiometers, and each one is going to be controlling one color of the LED. Next time, I'm going to probably next time I'll do a quick overview of the 8-bit version of this. And the only difference in the 8-bit version is I say 1, I put a 1 here on the left adjust result, and I just return ADCH. I just return the high byte. And that will give me the 8-bit version. Next time I'm going to show you, we're going to go back to the timer. I'm going to show you something about the pulse width modulation mode, which is the most useful mode of the timer. And you'll be using that to control the brightness of the LEDs. Okay, any questions?
So in order to control the other potentiometers, you just change it from 0 to 1 or 2?
Yep. Yeah, if you put a 1 here, you're reading the center potentiometer. If you put a 2 there, you're reading the leftmost potentiometer. That is correct. Which is one of the reasons this routine is really nice. Okay, cool. There's my mouse. There it is. Bring you back here. Okay, stop sharing the screen. Okay, any questions?
Not at the moment.
Okay, have a good weekend. Enjoy Monday off, and I'll see you next Wednesday. Blessings.
You as well.
Have a
Yeah.
good one, Professor.
Goodbye.